thrilled to be here and to talk about some new ideas for observing severe weather, tropical cyclones in particular. And we have a new approach that uses some really tiny satellites. So I'll talk about how that works and what advantages that offers. And let me just take you through what's the cartoon that's on your screen here. So we measure the Earth from satellites that are orbiting in low Earth orbit and geostationary, measuring weather. We've been doing that for many decades, and these systems make measurements of essentially the atmosphere is radiating very tiny amounts of energy, and we can measure that and relate that to things like rainfall and temperature and moisture. And then we feed those data into what are called numerical weather prediction models to generate a forecast. But there are some deficiencies in how those systems work, and we think that we can make those better. And one way we make those better is we make more frequent measurements. And we make more frequent measurements by flying more satellites. And we fly more satellites by making them cheaper and easier to launch and operate. So that's really what we're trying to do here, is to miniaturize these weather satellites, which are traditionally the size of a school bus. These are big billion-dollar class satellites, and we have miniaturized that into something that's about the size of a loaf of bread and weighs 10 pounds. And instead of costing billions, it costs maybe $1 million, and then we fly a lot of those. So the pictures you see on the screen, the things, I don't know if you can see my cursor, I can try to. So here is a hurricane. You can probably recognize there's the eye of the hurricane, and the satellite makes measurements that allow us to vertically slice this. So we can tell what's going on as a function of altitude, their rain bands, and the eye in the middle, and a lot of moisture around here. You can see rain over here. So I wanted to do a few things here. I wanted to introduce you to what a nanosatellite is, and even another term called a CubeSat. These are very tiny satellites that have come into play in the last 5-10 years or so, and how we can use those to advance weather forecasting. So let me get into it. Let me start with a little bit of an introduction, just to talk about, and I think this is fairly intuitive to all of us already, how important weather satellite data is and how often it's used and what impact it makes. So just a few notes on that. So, 300 billion weather forecasts used every year. So all of us fire up our iPhones or something and check the 5-day forecast and plan our week, plan our day, or it's information that we've come to rely upon as part of our daily lives. And there's all kinds of applications and mapping services that that we use that are driven by the forecast. NASA and NOAA, the National Oceanic and Atmospheric Administration, provide these data to all kinds of users and agencies. The Navy, for example, derives great benefit from knowing what the weather is, as you can probably imagine. And these data are used to help us manage and mitigate natural disasters. Right, so there's all kinds of uses for this data that has impacts on our society and economics and all kinds of things. So it's really important data, and there's always room to make it better, right? So we're always trying to make the forecast better, more accurate, into longer time horizons and so forth. So the current weather satellite enterprise, if you will, it uses two kinds of satellites, and the differences are how they orbit and where they orbit. So there are geostationary satellites, and these orbit in sync with the Earth. So as the Earth is rotating, the satellite is rotating in tandem with it. So it stares down at the same place on Earth all the time. The Earth rotation and the satellite orbit are synced up. Call that geostationary orbit. And there's also a polar orbit where the satellite flies closer to the Earth, and it's every 100 minutes or so it will orbit the Earth. And as the Earth spins underneath the satellite, it will map out a swath, and eventually over the course of a day or so, the satellite will map the entire Earth. So it's kind of a global picture. And on the left part of the slide, I just wanted to give you a sense, and I put a scale there in time for very fast time scales at the top and going to slower time scales at the bottom, from minutes to days to seasons to decades and centuries. And to give you a sense of the various things that we care about, things that are very dynamic and happen fast, like tornadoes and flash floods and connective activity and earthquakes, which are happening pretty quickly, to things that take longer to develop and longer to develop a time record, climate change at the bottom, right? So we're trying to cover this very vast, many orders of magnitude time scale, and we typically do that by combining geostationary orbit satellites and polar orbit satellites. That's what NOAA does. And if you get down into the details of that in terms of how you architect the system, we have all kinds of sensors that observe in different frequency ranges, from the visible to the infrared and the microwave, and they all have their various advantages and disadvantages. For example, the visible and the infrared are very sensitive to temperatures, but they're blocked by the cloud tops, right? So if you're in space and orbiting satellite looking down with a visible camera over a storm, you're going to see the tops of the cloud. You won't be able to see down into the storm itself. Whereas the microwaves actually can penetrate down into the storm, but would usually with coarser spatial resolution, right? So these are all these trade-offs that we play with when we design these architectures. Okay, so that's kind of a broad brush picture of how we use weather satellites and the pros and cons. Now, how about nanosatellites and cubesats? So on this slide, I wanted to give you a sense of the size of the satellites. So at the top of the chart, we've got really big satellites, school bus size mega satellites. And this satellite right here, if you can see my cursor, is a picture of a polar orbiting NOAA satellite. So again, a school bus size billion-dollar class satellite. And, we fly satellites that span the range from the school bus size to, the size of a car to the size of a washing machine for smaller satellites, which maybe make images of the Earth and things like that. And more recently, there's been this explosion of nanosats, which are about 1 to 10 kilogram size. So, 2 to 20 pounds, and even smaller picosats and even femtosats, which could be even a chip or a wafer that flies as a satellite. And the power of these nanosatellites is this CubeSat reference design that came out over 20 years ago as an educational tool. These two professors at Cal Poly and Stanford built this as kind of a standardized way to allow students to design, build, and test and operate satellites that could be designed and built and flown in a couple of years, right? So they could do this as part of a thesis project and see it from, cradle to grave and write a thesis on it. And one of the powers of these CubeSats, and here's a picture of one. So a cube gets its name because it's 10 centimeters on a side. And you can buy kits or electronics to put these things together. And it's a standardized process. So all the parts that you buy are designed to fit within these things and connect together and work together. The power systems and the avionics and the computer boards and the batteries and solar panels and all kinds of things. You can go off and buy these commodity parts and put these systems together quite easily and at low cost, right? So we saw this come to pass. Remember, I graduated back in 2002, just when this was taken off, and I was asking the question, what would it take to try to put a weather satellite instrument on one of these things? And that kind of started this whole thing for me. I've been going on this path for, over 10 years. So I'll come back to this. So this was the motivation to try to put, miniaturize a weather satellite, put it on one of these very small commoditized CubeSat buses, they call them, CubeSat platforms, and then launch a lot more of them. So the regret of the NOAA big school bus size satellites is that they cost so much, we don't have very many of them, right? So we've got about 2 of the geostationary satellites, and we've got about 2 of the polar. So when you have 2 of these polar satellites and it takes 12 hours to remap the same point on the globe, you're waiting about 6 hours. If your polar satellite that's flying a microwave sensor on board where you can penetrate into the storm, you've got to wait 6 hours before the next satellite flies over and takes another image. And there's a lot going on in that storm. It's developing with dynamic scales on the order of minutes. So you're missing what's happening there, and that's making the forecast worse because we're not getting all the data as it evolves on this time scale of the storm. And the geostationary satellites don't have the microwave sensors that we need to penetrate down into the storm. So I'll come back to that, but those are some of the deficiencies of the current systems, and we can overcome those in principle by flying a lot more. We can get flying a lot more by using these low-cost CubeSat platforms. It's kind of the overarching idea here. So now let me talk about hurricanes. Okay, and as you can probably imagine, it's really difficult to try to observe effectively a tropical cyclone. A hurricane is a type of tropical cyclone. So tropical cyclones are typhoons and all kinds of things. Hurricanes are in around the U.S. we call them hurricanes. So here's a picture of a geostationary image of the top of a hurricane, and this is showing essentially this is Hurricane Dorian, showing the top of the storm. And just some statistics on the right about how impactful these storms are. So one example, we've got 73 fatalities, $5 billion of economic damage. So, that's just one storm, right? So it's pretty easy to motivate. We need to do a better job of forecasting so we can warn people and do the disaster management to get them out of the way and have warnings that people believe and trust. We don't have false alarms and things like that. So they're very difficult to observe, and the data are, of course, very important and impactful on our daily lives. So the other component of the story is that we have a lot of tropical cyclone activity, and it's increasing every year, right? So here's one example. A few years ago where we had, at one time, 9 storms that were either raging as hurricanes, a Cat 3 or a Cat 4, or a depression that's about to turn into a hurricane. So it's a global problem. You need to architect a global system that you can track all these at the same time. So taken together, that's pretty challenging, right? You have a very dynamic storm where you need high spatial resolution, high temporal resolution, and you have to observe over the entire globe. So it's, again, a very challenging problem to address from the standpoint of designing, satellites to measure all this stuff. So in terms of, the key observables, the variables, what do we need exactly to observe from a tropical cyclone, from a weather satellite orbiting in space? And there are a couple of key fundamental thermodynamic variables, if you will. So one of these is the amount of moisture, the humidity in the air around the storm. And we need to measure that in 3 dimensions, the vertical dimension and the horizontal dimension. And it's the warm, moist air that fuels the storm, that gets it spinning up and going. So that's one, is humidity or moisture or water vapor. Another one is temperature. So the image here is a cross section through the eye of the storm, and something really interesting happens in the eye of the storm. And so the red colors at about 6 to 8 to 10 kilometers are warm relative to the other parts of the eye, right? So there's this warming aloft, and that warming aloft, something we call the warm core anomaly, is highly correlated to intensity. So if we can measure that, we can measure something about the intensity of the storm and maybe even potential to further intensify or dissipate. So that's the second thing, temperature. So we've got moisture, now temperature. And then the third one, you probably guess this one, is the rain. How intense is the rainfall? And what's the structure of the rain bands? So you've got this spiral structure of the rain bands coming off from the eye. And the asymmetry in that tells us something about the intensity and the potential for intensification. So the shape of the storm, and in addition to how hard it's raining, is very important to put together the entire picture of what the storm is doing and how it might change, either intensify or dissipate, and how we can predict that with a forecast. So we need to measure all of those quantities: the temperature, the moisture, the precipitation, in 4 dimensions, right? The horizontal dimension, the vertical dimension, and the 4th dimension is time. We need these updates very rapidly. So we want to fly over the satellite and then fly over with another satellite, not 6 hours later, but 10 to 20 to 30 minutes later, or an hour later. We need to do much better than that. So that's really the motivation for a new type of observatory that can provide all these variables with very high resolution and get the temporal updates much better than what we have today. So you're probably aware there are a lot of good ways to measure rainfall and tropical cyclones. So we've got really nice radar networks on the ground, right? So we don't have these over open ocean. So they don't really help for hurricanes. It's possible to put a radar on a satellite, but it's really hard to get a wide swath radar to work effectively on a satellite. It takes a lot of power. It's very expensive. So it would be great if we could do it, but we don't have the technology yet to produce those at scale. We have a small handful of those. We can drop Temperature sensors out of aircraft. You've heard of the Hurricane Hunter aircraft and things like that, where they fly through the storm and drop instrumentation and measure as they fly through. The problem with that, those work great when you have that, but the sampling is pretty sparse. You don't have as many measurements as you'd like. So the satellites is a great way to get a big, broad picture of what's going on, rather than kind of a small scale measurement you'd get from an aircraft. I mentioned the GOES, the geostationary measurements, can look down, but you get just the top of the storms. You see the top of the clouds. You can't penetrate into the storm itself to get the temperature and the moisture things that you need below the cloud tops. So this red box around passive microwave sounding is kind of a nice compromise in the microwave region of the electromagnetic spectrum, from about 10 gigahertz to a couple of hundred gigahertz. There's a lot of interesting information in that region of the spectrum. We can get the temperature, the humidity, and precipitation from the microwave band, and they can penetrate down in there below the cloud tops. And I'll say a little more about this coming up. Okay, so one little piece of magic with this is how we derive temperature or moisture as a function of altitude. And this is kind of neat, all right? And so before I explain this slide, let me tell you a story, okay? So back in World War II, 1940s, the US and Great Britain were trying to figure out how to make radar work. And they were testing a system around 23 gigahertz. And it worked great at 20 gigahertz, it worked great at 21 gigahertz. At about 22 and a half, it stopped working completely. And they tried to figure out what's going on. Why did this completely stop working? The instrumentation was fine. And they figured out that the atmosphere, the attenuation of a radio wave through the atmosphere depends on frequency, right? So the water vapor molecule, it turns out, has a resonance at about 22 and a half gigahertz. So if you shine a beam, if you put a radio wave through the atmosphere at that particular frequency on that absorption line, there's a lot of attenuation. It basically gets absorbed by the atmosphere. So they figured that out, and it's a trait of Mother Nature that there's these absorption lines due to water vapor and oxygen at these very specific frequencies. And there, several Nobel Prizes were awarded to the folks who discovered this. So we use that to our advantage in weather sensing. So the example I'm showing you here on the slide is one particular line due to oxygen. It's at 118.75 gigahertz. So at that particular frequency, there's a lot of attenuation because you're right on that oxygen absorption line. And the cool thing is if you turn the dial and move the frequency away from 118.75, either lower or higher, the attenuation drops. Okay, it kind of rolls off, right? That's the peak you see here at 118 is the highest attenuation, and then it rolls off the lower attenuation as you move away in frequency from the line. So what we do from a satellite is we have different channels. We put a channel near the line, and that channel is going to sense areas that are very high in the atmosphere. And we put channels away from the line, which will sense areas close to the surface, low in the atmosphere. So by walking off the line toward the line, we move up in altitude, right? So there's this relationship between the frequency that we observe, the channel, if you will, turning the dial on your radio, essentially on your weather satellite, and moving up and down in altitude. So we can do that in temperature using the oxygen line, and we can do that for water vapor using the water vapor line at 183.31 gigahertz. So when I get into this instrumentation, you'll hear me talk about the 118 channels, 118 gigahertz channels, and the 183 gigahertz channels. And this is why, because we're using this really cool trait of the atmosphere and attenuation. Okay, so I talked about the traditional NOAA weather satellites. This is a picture of a polar satellite. Again, this is a very large, 4,000-pound school bus size satellite costing billions of dollars. You have to wait many hours for the next one to fly over. What we're trying to do here is essentially miniaturize that. Okay, take advantage of technology to miniaturize the weather satellite the same way that a cell phone over the last 30 years has gone from something you have to carry around in a wheelbarrow to something you can wear on your watch, right? These technology advances, we can use that for weather satellites, make them much smaller, make them more affordable to build and easier to launch. And if you can do that and scale it up, then you can revisit things on the order of minutes instead of hours. So that's the motivation. And we've been working on this technology evolution at MIT with our partners for the last decade. And just to take you through that really quickly, so the key parts that you need to make this work are essentially what we call a receiver. That's the piece of electronics that takes in and measures how much radiance is emitted from the atmosphere. And there is very small quantities, right? We're listening to the atmosphere. So there, the gain that we need in the receivers to do this is about a factor of 1 billion or more, right? So very sensitive receivers to measure that. So we worked with some partners down the road from us at UMass Amherst. They had just the thing that we needed turned out for a radio astronomy experiment. So that was a great partnership. Then we started working with the Aeroastro department at MIT campus to try to figure out how could you accommodate an instrument like this on a very small satellite. Remember, this thing has got to rotate. It's got to scan across the Earth and make an image as it's flying. So it's rotating about once every 2 minutes as it's flying along. So you've got to keep your spacecraft stable and support this rotating payload. So that was a challenge. We built and launched the first one of these, Micromass 1, in 2015. And here's a little animation at the bottom showing you how the payload is rotating as the satellite is flying. And we gradually improved and incrementally learned a lot of lessons on how to do this. And it's culminated in what we call our Micromass 2A CubeSat in January of 2018, where we put all the pieces together and figured out how to do this and made the world's first image like this from a CubeSat. And it worked great. So here's an image near 94 gigahertz from our Micromass 2A satellite. And comparing this to the $2 billion NOAA satellite, which has more than just microwave sensors on it, by the way. There are about 6 sensors. But our data is comparable to their data in a much smaller size and a much lower cost. So this was the real breakthrough that proved to us that, we can do this. Let's make a constellation of these things and launch a lot of them, scale them up, and achieve that revisit rate that we want, which is on the order of, tens of minutes instead of hours. So that led us to the TROPICS mission. So that was the breakthrough that showed that we can do this. Let's scale it up, build the constellation. So we wrote a proposal to NASA Science Mission Directorate, the Earth Venture Program, and they selected us to do this. So this is a great idea. Let's try this out. So I lead this mission in collaboration with a great team. So at the bottom of the slide is all our partners, and it spans NASA and NOAA and a lot of universities, MIT, Wisconsin, Miami, Tufts, a lot of great folks helping us do this. And what we're building in the lower right photo there, so there's 6 flight units. We actually built 7 of these. We built something we call the qualification unit. We built that one first to prove out our design, make sure that we knew what we were doing before we cranked out 6 more. So we built 7, 1 qualification unit and 6 flight units. And the gold block on top is the payload that spins here. This red cap is just removed before flight. We're trying to protect the antenna in there. So we measure in 12 channels. Remember the channels, this is the block of frequency that we choose very carefully around those absorption lines. So we have channels near 118 for temperature, channels near 183 gigahertz for water vapor, and then 2 imaging channels that kind of bookend these, one at 90 and the one at 205. So we're working with a lot of commercial partners. I mentioned that you can buy these CubeSat kits, right, with the batteries and the power supplies. And there are companies now that make very sophisticated, high performance, high reliability CubeSat platforms. Blue Canyon Technologies in Boulder, Colorado is one of these companies. So we work with them. They made the lower half of this thing, this 2U they call it. It's the platform that accommodates our spinning payload. And we built this at Lincoln Lab. And we actually decided to launch our qualification unit in June of last year. And that's typically something that you don't do when you build a satellite and you build a qualification unit. What the whole goal of the qualification unit is to test it and even over test it to make sure that when it will withstand the rigors of the launch and the rigors of the environment in space, operating in a vacuum over temperature extremes. But it's so affordable to launch these days. The SpaceX Falcon 9s are going up every week or so, and they offer ride share. Essentially, they will put you in the trunk and pop you out when the main payload goes, and you can buy these things for on the order of $100,000, $200,000 for a launch instead of the normal SpaceX Falcon 9 launch is something like $65 million, right? So 100K is a pretty good deal if your satellite is small like this and you can do that. So we launched the qualification unit as kind of a dress rehearsal, a dry run to check everything out on the mission before we flew the Constellation. And that worked fantastically well. I'm going to show you some imagery from what we call the Pathfinder, and that is great. So we were very excited. And then we had a setback. The first setback of the mission happened this year. We tried to launch the first two. Remember, we have 6 of these flight units. We launched 2 of them in June out of a beautiful afternoon in Cape Canaveral, and that launch failed to reach orbit. We were about a minute away from orbital insertion velocity and apparently ran out of fuel. So we're bummed about that. But the good news is we have 4 left, and we built in some redundancy in our mission so we can still meet our mission objective, which is a 60-minute median refresh. Again, that's much better than what we get today, which is about a 6-hour. Even with 4 satellites, he's got to go into a very specific orbit that I'll talk about. So that's kind of the thumbnail sketch of the mission. I'm going to fill in some of the details here. So one detail are the science objectives. So the TROPICS mission is a science mission. It's not a technology demonstration mission. This is full up science. So we have hypotheses that we are trying to illuminate with this data to answer some basic fundamental science questions that will ultimately lead, we hope, to better forecasting. So I just wanted to give you a sense of what those questions are. So we're looking for relationships from the things that we can measure usefully with these microwave observations to the storm variable. So we're looking at precipitation structure. I mentioned the symmetries and the spiral rain bands and how that might be a marker for evolution of the storms. We want to look at the precipitation intensity and relate that to the overall intensity of the tropical cyclone. And again, we want to understand how the moisture in the environment around the storm helps to drive that either to intensification or dissipation. And having learned lessons from those 3 questions, we can then turn around and improve how the forecast models work and make better forecasts in terms of where is a hurricane going to go. We've already, we see these projections and the cones of uncertainty, right? The track is going to go here, it's going to intensify. So we want to have better forecasts of the track and the intensity so we can warn people to get out of the way, right? That's really the end game here is better warning, more accurate disaster management. There's a lot at stake here with these measurements. So a few more details on how the mission is going to come together. So the animation that's running in the bottom middle panel of the screen shows the swaths as the satellites are orbit. The payload is spinning, so you get the swath across the Earth. It's about 2,000 kilometers wide. And they're very specific orbits that we need to make this happen over the tropical cyclone belt. You don't have tropical cyclones beyond, poleward of about plus minus 40-degree latitude, right? So we don't need any observations there for tropical cyclones. So we put these inclined orbits up there, so we're always over the tropical cyclone belt. The CubeSat is shown in the upper left. So this is called a 3U. Remember, 1U is a 10 by 10 by 10 centimeter cube. So this is essentially an aggregate of 3 of those. So it's about 36 centimeters long, 10 by 10. And you see the rotating payload here. This circle called the aperture is the antenna. So this captures the incoming radiance at those frequencies from 90 to 205. These are radios. We get the data back down to Earth with a radio link at about 2 gigahertz. So we have ground stations around the globe that receive the data from the satellite and broadcast up to send commands and so forth. There's a solar panel here that is actually able to rotate and track the sun. And the spacecraft bus is able to roll to keep the array on the sun. So it's a very sophisticated system with avionics and batteries and the power system and fault tolerance and memory on board to store the data and broadcast it down. A lot going on there. So I mentioned the orbits need to be at 30-degree inclination. That's why we need a special dedicated launch to get us up into the orbit that we need to put us over the tropical cyclones. And our requirement is this 60-minute or better median refresh rate. That's what we're going for. Now the data, as it comes down from the satellite, moves from a commercial company called K-Satellite. They operate the antenna dishes. They look up and point as our satellite flies over. They'll track the satellite and downlink the data. The data then comes over to MIT, Blue Canyon to MIT to Wisconsin for the data processing and the algorithm generation and product generation, then out to the general public through something called the Goddard disk, which is an archival system. So if you want, you all can get data from this once it's launched and look at it. And certainly the forecasters are very interested in looking at the data. So here are just a couple of details on the 12 channels. And I won't go through this in much detail unless there are any questions there, but just to point out again, they're imaging channels near 90 and 205, and the 118 is for temperature, the 183 are for water vapor. So I wanted to show you that these, there's a channel that's very close to the line at 118.75, then we gradually step away from the line to penetrate deeper into the atmosphere and look at the surface. And there's a channel near the line at 183, and then we gradually walk away and look at the surface as opposed to the upper atmosphere. The horizontal resolution, so the beam width, if we look at, we'll take one instantaneous measurement, the footprints are fairly large. They're 24 kilometers for the temperature bands and 17 kilometers for the water vapor band. So the spatial resolution, is not exquisitely great, like 100-meter class, but it's big enough to resolve the eye of a hurricane and image the rain bands and reveal the structure that we're looking for. So it's a good enough measurement. We penetrate the cloud tops. We're sensitive enough to the phenomena that we're trying to measure, and we can resolve hurricane eyes and things like that. Okay, let's see here. So I just wanted to point out how we calibrate this thing, and that's a challenge. So we measured the radiance, but we need to convert from kind of the engineering units, the voltage or the counts the detector measures, and convert that into a temperature. And the way we do that is, again, we're rotating every 2 seconds. We scan across the Earth, and then we look away from the Earth into the space background, if you will, right? So we're looking away out into space, which turns out to be very cold, and it's a very stable reference. It's about 2.7 Kelvin. It's very close to absolute zero, but it's very cold, very stable, and we can use that as a calibration point, a very cold calibration point. And so the atmospheric temperatures that we measure are much warmer than that, of course. We're measuring from about 230 Kelvin to maybe 330 Kelvin. So we need a warm calibration point. And the way we get that is, as we're scanning through the cold space, we turn on a piece of electronics on our receiver that generates a noise signature that we know very accurately. And we use that for a warm calibration. That's called a noise diode that we use. So that's how this is calibrated. So every scan, we look at cold space. We know that's 2.7. We look at our noise diode. We know that signature very well. It's about 300. Then we can calibrate the scenes that we measure from the ground. Okay, so the technical challenge of pulling this off really centers around making the payload small, making this instrument very tiny. So the payload cube, and remember this is about 10 centimeters on an edge here, there is a trade-off between the antenna size. So we're motivated to make the antenna as large as we can, because that improves our spatial resolution. But the regret of making the antenna big is that we have less room for all the electronics that we have to put around here, for the receivers and the control electronics. There's a flight computer in here and a motor that spins it. So we're trying to make the antenna as large as we can. This part here is the antenna. But keep enough room for all the electronics that must go around here, and these kind of snap together modularly into this cube that forms the payload. So here are some photos of some of the flight hardware. The antenna system is very sophisticated. It combines these beams from the two frequencies, the 180 and the 205 and the 90 and the 118. This circle here has tungsten wires that are strung very tight. They're about 20 microns thick. They're plated in gold, and there's a lot of these things in a grid, and we can use that. That gives us a very specific polarization signature. So one frequency will go through that, and the other frequency at a different polarization will bounce off of that. So what's going on here is this beam is going through the grid to the antenna and to the Earth, and this feed horn here is bouncing off the grid, right? So we're able to combine those two beams into a single footprint, which is a very nice way to do it. Here's the receiver that the folks at UMass Amherst built for us based on their radio astronomy experiment that was at very similar frequencies. Here's a very small and flat, called a pancake motor with a hole in the middle. And you're wondering, why is there a hole in the middle of this? Well, that's to get the data back to the spacecraft. So the payload makes its measurements, digitizes those, and then there's something called a slip ring that allows us to transmit this electrical signal through a rotating joint back to the spacecraft bus so we can transmit it down to the ground. We've got back-end channelizers that make those 12 channels. This is essentially the flight computer that operates everything. And here's the receiver for the water vapor channels. So those are the parts that go together. And they all are assembled in this unit. This is our flight unit. It shows everything together: the antenna, the receiver electronics, waveguides to move the signals around. And this works really well. I have to balance this thing. Remember, this is spinning, so we don't want the spacecraft to wobble. So it's balanced like you balance your tires when you go to the dealership to get your tires on. They balance them. We have to do the same thing here so we don't wobble the spacecraft. So there are actually weights put around this thing to keep it all dynamically balanced. So here they are. So here's the qualification. This is the what we call the Pathfinder with a spinning payload, and the array is turning. If you can see, if you look carefully in our 6 flight units. And we launched this, as I mentioned, on the SpaceX Falcon 9 back in June into a 530 kilometer low Earth orbit. This is something called the sun synchronous orbit. So it's orbiting and crossing over the equator at the same time every day because its orbit is locked into how the Earth is rotating. And the data from this has been spectacular. I need to wrap up here pretty soon here, but let me just show you some pictures. So we launched this in June. It took us, there were 90 other satellites on that launch because it's a ride share. That's the deal, is they have, they basically aggregate a bunch of CubeSats together and then dispense you all out into a big cloud of CubeSats, and takes you a while to find your particular satellite and start talking to it. So we did, and right out of the gate, we got spectacular data. Here's a global image near 92 gigahertz, and you can see all the fine scale features of water vapor down here in the southern hemisphere, all the very nice temperature signatures. So this worked great right out of the box. We had a lot of really nice storm imagery. This is one example. This is Hurricane Ida approaching the Gulf Coast. So you can see it's a very organized storm here as it's making its way toward the land with a very distinct eye and a spiral rain band. And as it makes landfall, the organization starts to break up, and then all the rain comes out as it comes up over the landmass. So we can see all that with Pathfinder. So again, this is this 12-hour cadence I was talking about. So we make one image, and we have to wait 12 hours for it to fly over again. So what the Constellation will do when we launch that next year, is it'll fill in these temporal gaps. We'll have much more intermediate frames, if you will, in this video of the storm as it is kind of evolving. Let's see here. So here is an interesting picture. So here is Super Typhoon Mendel, and we flew over this with the Pathfinder, and the big NOAA satellite also flew over it. And we're showing our image versus the big guy. Remember, this is the $2 billion guy over here. And I humbly submit to you folks that our image is pretty good, right? We can very clearly resolve the hurricane eye. We get these really spectacular deep blue spiral features off of the inner rain band, the inner eye wall, which we were missing on the current state-of-the-art satellite, and this great depiction of the rain band. So it's spectacular imagery. This 205 gigahertz channel has never flown before, right? So this is 183 plus or minus 7, so it's up to 190. We go even farther with our system, so it's really an ideal observatory for measuring the structure of the storm, resolving the eye, and so forth. So we're very happy with how great this data is in this first of the kind. Right down here, just some other shots. Here's Batsarai. Again, very clear delineation of the eye and the rain bands and the spiral structure and so forth that you see here. Here's Cyclone Amnati at 2 frequencies at 90 gigahertz and 205. And the really cool thing here is if you look over on the right side, there is an eye within an eye, right? So what's happening, called an eye wall replacement cycle. The eye is breaking off and then recycling. We caught this thing right in the middle of that, and we can resolve actually this mini eye. This is the first time, to my knowledge, that a cross-track payload like this has ever been able to resolve this. So this is a breakthrough for us, really, really cool image. And again, you see the spiral structure, really nice imagery from the Pathfinder. This is in February of this year. So we can do more than image tropical cyclones. Here's an example of snowfall. So it turns out that our 205 gigahertz channel is very sensitive to the snowfall. Couple of shots of our data versus the NOAA satellite data, and we're more sensitive to snowfall than they are due to the use of this higher frequency channel. So a very good snowfall measurement system. We've imaged tornadoes. This is a very strong line of tornadoes moving over the Midwest last year. We were able to image this with our satellite quite nicely. So very sensitive to these severe weather events. And we can even resolve climate signatures. So these are monthly averages of the temperature at about 6 kilometers, 20,000 feet, if you will, from August to September to October to November. So as the Earth is tilting on its pole, there's this gradual southward migration of this warming as that's happening. We can see that very clearly in the Pathfinder data. So it's sensitive to even very subtle temperature changes over monthly timescales. So I have a couple of charts that I'm going to go through pretty quickly. We do all kinds of assessments to convince ourselves that the system is operating as it should. We want to know geolocation is essentially, how do you know where the beam is pointing? You've got a satellite or solar array is moving and the bus is rolling and the payload is spinning. How on earth do you know where the beam is looking? So we've got software on board that manages all that, and we test that. What we do is we fly over coasts many times, okay? And we look at our beam, because there's a very sharp contrast in the data when we fly from ocean to land. These coastal crossings, it's very apparent in the data. So when we do that tens of thousands of times, we can put amass statistics on where the coast, we know where the coasts are, so we can line that up with our data and figure out how well we're pointed. And we're pointed to a very small fraction of a footprint. So that's great news. That means that all our software that's doing the accounting of all those different pointing vectors is working great. We look at our absolute accuracy. And the point here is that we compare our measurements that I'm showing you what we're calling O minus B. So O is observation and B is background, which is essentially something that another measurement that we trust. We want to make sure that we match the measurement that we trust. And one challenge is that the spacecraft is constantly going, as it's orbiting, it's going in and out of sunlight. On one half of the globe, it's in the sun. On the other half of the globe, it's out of the sun, getting hot and cold continually. So we need to make sure that our calibration is working over that entire range of getting hot and cold. And that's what this is trying to show you here is the instrument temperature is oscillating back and forth. The departures from the data that we trust are very small, which means that our calibration is working very well. So this is our 90 gigahertz channel, the temperature bands. The red lines are essentially our requirement. So we want to be as small as possible and the water vapor. So we're working very well, and we're working very well even as we're going in and out of sunlight. So that's good news. Just to give you a sense of the products that we generate. So I mentioned that the temperature and the moisture profiles. We assess those to make sure that the quality and the fidelity is what we think it should be. And it looks very good. We have tropical cyclone intensity products that are derived from that warm core anomaly. So as the storm intensifies, the pressure inside the eye actually drops as the intensity increases, and we can track that very accurately with the TROPICS data. That's good. And our rainfall product is looking very good too. So these are the global rainfall product compared to other sensors that we trust that have been operating for a while. So we're doing all these assessments of the products that we derive from the data, and they all look great. So one more thing in terms of where is this all going? So given that we've proven that the Pathfinder is a great new addition, we'll have data next year on the Constellation. Commercial sector has taken note of this, and they want to use this technology. So we're working with this company. They're based here in Boston, called Tomorrow.io, and they are putting up their own weather satellite constellation, something that was kind of unthinkable not that long ago. But these guys are putting up dozens of their own satellites, one of which will be this kind of a satellite based on TROPICS technology. So we're helping to transfer all this technology that you guys all paid for as U.S. taxpayers, and to get that into the commercial sector so they can essentially scale it up and make the forecast better. And NOAA, of course, can use this data if they want that. So it's starting to proliferate and become part of our daily lives. We're very happy to see this technology proliferate like this. So let me wrap up, make sure I have some time for questions. So we're very excited about the TROPICS mission. We launched the Pathfinder, and the data is spectacular. We're working great to this day. We're still working fine. We're over 7,000 orbits. We've got great pictures of Hurricane K over California last week, and Danielle and Earl. So that's working great. We have launches of our remaining 4 CubeSats next year to get the Constellation up. So we're very excited about the Constellation data. And I mentioned that we're transitioning this great technology, U.S. taxpayer-funded technology, out to the commercial sector so we can all take advantage of it. And we recently won an R&D 100 award. We're very proud of this based on the technology from TROPICS. So with that, I'm happy to stop and take any